here we have one engine from Argentina, which is going to perform an experiment. And the people from Canada, Jordan. And here's Saskatchewan. And that's Saskatchewan you're looking at, Saskatchewan. Okay. And here we have the speaker here. Joseph, yeah. I think we have to speak loud. Hi. So, Mr. Montreal, from here, what we do instead of the shed like the look at characters, look at precise information about organization gathered. That here because we have give former scientists here in Canada, and we have strong collaboration. So we start then with this. What we do first, Lisandro, can you take control of the experiment?
Yes,
okay. This the sample you're going to study?
Yes.
Okay.
Here I am in theoretical physics and chemistry in La Plata, and I will do a measurement of the use of colors silicon oxide material. What I'm going to do is you see in the screen there. Choose which sample I will measure.
So you first do you choose what you see here, interception of the area detector on the conical scale. Here we see the intensity of this. And here we have the moving sample, putting the position to start a measurement. Right? We're doing that from Argentina, and you see now the spectrum coming up. This is a prototype of the system. I will explain later how this works. Now, start the position of the measurement, and okay. This is a sample, okay?
We are ready?
Yes.
Just the name of the file.
Okay.
And just what where we will get the position. Second.
Okay.
Just click and do.
Okay. So the red light turns continuously. It means that we have that. So once the X rays is the best, very fast measurement, you will see percentage of position.
Maybe so you are in the wrong sample.
You are
in the capsule.
You capsule sample.
We'll change it again.
Okay. Another sample.
You see it's moving.
See, there it's moving. Okay, now we see here. This is a filled spot with a sample. This is what's called. It's a spot with a powder of lesothiazide. It's a system that is used for drug delivery, biosensor, and many other things. It was synthesized here between Canada, Argentina, Brazil. Definitely has a collaboration also in this systems. And what we do is once we look at these cones, we can recover the structure of. Oh, there it is, right? So what you see, the circles are intercepted. The intensity of these spots basically allows us to look at the structure of the measurable scene. Right? So, can you please send the control to Canadian light source?
Yes.
Okay. So what we're going to do, this experiment was down there in Argentina. Now what we're going to do is an experiment being controlled from our fellows there. Okay, can you do the sample of petroleum? Okay. So now we see that it's moving into the position. You see that the sample is actually quite black. It's petroleum from the pre-salt reserves. He is controlling. Yeah, exactly. He's controlling actually the sample. So he's putting the sample into position. There it is, the sample. It's a black spot. It's very thick oil. And here, okay. So,
Harry, just to be clear, this is the measurement right here.
yeah, he measured right here.
in Canada. Next, we're
So,
going to Argentina.
see, that's this intensity basically on noses. It's not as sharp as peaks like the other one, but what you can see is that there's a distribution of a molecule called phosphocene, which is a technological problem for the result, right? And this kind of technique can help us. So,
reduces the viscosity of that one.
yes, actually, if you study how we can handle this molecule, you can reduce this problem.
Sample is here, it's measured here, and it's controlled.
Now, this was a prototype. We had a local company here with a group that did this. And once we wanted to move from a prototype for a real system from we studied different options of different systems being employed in different platforms that synchrotrons are for. In fact, you can count in one hand the number of initiatives like that. And the Canadian source had an initiative which they call Science Studio. We found out that it was mature and it was robust system, right? So instead of we started to develop a new system from our prototype, we decided to put our forces together in a single system. So what we do is now we are porting our system to the single form. So we have one single platform for, and we hope to be this used in other places also. So what you see there is a picture of software in development, So it's the same kind of experiment that we done into the Science Studio, which is the platform developed by the Canadian source, right? The product of the Canadian source, and we are in
So that's a two-part operation.
exactly. We hope so, yeah. Apparently, we creating resources which I started to use, carefully starting to use also. So I hope that this becomes some kind of standard in all remote operation. This is something that is actually going to be more and more used because you have a wider reach for your beamline and you can actually be complementary with other systems and you can reach other researchers and students as well.
Is this machine operating 24 hours a day?
Yes.
So it's
Pressure, exactly.
And this is being funded from our side.
From Petrobras, yeah. You saw the sample was actually from Petrobras, and all the system is being funded by Petrobras.
So one of the practicals is viscosity of pre-salt.
Exactly. And so once we started to do this, we still have the system working here on the Science Studio, but what we will do is we are going to use the Science Studio to control the beamline there in Saskatoon, right? So now we're going to pack Science Studio. Okay.
Yeah.
So you can see there.
Is in Canada.
Ready? We are now controlling. This is a biological tissue. And the idea here, the experiment being there, the concentration of titanium oxide seems to be a relation that we can see. So there we're going to use a different fluorescence. So basically shine the sample with beam. What you can see, the green dot is the beam, and the red square is the reading that we're going to see.
We're going to have titanium oxide.
Exactly.
What will it show?
What we shine with dark X-rays, and every atom of the sample we really need to with the fingerprint. And you know the fingerprint when the oxide changes. It's an energy, emits energy, right? An energy around 3 kV, so we know where is that. How do you know? You see peaks. We were doing spectrum and you see peaks of the spectrum every point. So, by every point of the spectrum, we can do a map of the situation, so that's what you're going to do. So, we start our experiment. Yes. So, other than that.
That's the very important.
And keep your focus. Yeah.
Keep your focus.
So,
Here is set up.
So what you're going to do is to press start. And then you can write the name of your scan. You can put your name on it if you want, just without spaces. And enter. Yeah. Okay. And there we go. Now, you can look at. You see the room moving? It's going to start. Or it jumps from one place to the other. Now it's going to jump to the left corner. Let's wait here. Okay, there you are. So now you see that the green dot is point. And every point that it goes, it does a spectrum, like the front. You see the peaks.
It's a slice, eh?
Yeah. So what you see is that one of these points, you see a spectrum that is live and it's coming from.
What's that big, tall, big beam force?
Oh, it's a concentration. In this case, it's concentration of iron. But we have different elements.
Union oxide,
Yes. So basically, then you can probe the concentration of that. And this is the experiment that is being done. So you see, it's very complementary to what we do here with the structure. There you look at concentration of chemicals.
Each dot an atom.
No, each dot is a point of gas. Actually, number of photons emitted by the atom. So what happens? You shine sample each atom with the number of photons, right? Absorb the photons and re-emit with a lower energy, right? It's
testing. And you're looking for.
actually, we're looking for concentration of the there is a suspicion. I guess Emil can tell you more about this. Emil, can you explain more about this?
Why do we worry about So it's a marker for Crohn's disease.
This full scan. So when you see the peaks is where you have more to in the tissue.
It's very interesting. On what technology is this in advance? How do we measure Crohn's disease in the present time of this? We take a tissue sample, put it under a microscope,
Yes.
and it doesn't give you enough specificity.
Yeah, I guess that's what, as any kind of biological studies, you have all possible answers for the question. So this is one possibility. Am I right, Emil? About what other kinds of diagnostics you can have for the Crohn's disease besides the microfluorescence? Now, it's very important in this kind of experiment that you have a microbeam. So this means that you need an accelerator, like the Canadian source, right? Or the Sirius that we're going to build. You're going to get an information. So third generation light source, right? You need a very tiny microbeam. So the smaller the beam, the more resolution you have in your system. And this kind of collaboration that we're doing here will benefit both sides. What I know is that what we're going to do from our there is the science. It's going to happen also in work for the drop-out sector. They're going to use at the same time. So you're going to learn from
Great. Thank you.
Thank you.
Let's thank our Argentinian friends.
So, is it cool?
Bye-bye.
Thank you very much.
Obrigado.